So it's my great pleasure to introduce Yejin Choi, who is the invited speaker this afternoon. So Yejin is an associate professor at the Paul Allen School of Computer Science and Engineering at University of Washington. And she's been running over the last few years one of the, I think, most interesting lines of work in natural language processing. Her recent work focuses on integrating language and vision, learning knowledge about the world from text and images, and modeling rich context for natural language generation, and also dialogue using this kind of techniques. So she was among the IEEE AI Top 10 to watch in 2015, and she got a few other awards, and I just want to mention one award that she got recently. She was one of the faculty guides for a team of students from UW that won the Amazon Alexa Award, maintaining a dialogue of, I think, over 10 minutes, so, which is quite impressive. So it's my pleasure to introduce Yejin, please.
Okay, so to briefly motivate this talk today, I'm going to share our experience with the Alexa Prize Challenge. So the goal of this challenge was to create conversational AI system that can make a coherent and engaging conversation with humans for more than 20 minutes. The good news is that our team at UW was the winning team of this competition. The bad news is that none of the teams were able to make this grand challenge of making 20-minute conversation. Ours lasted slightly over 10 minutes. And furthermore, what works really well for other kinds of tasks with deep learning, using brute force more data and deeper neural networks, somehow didn't work out well as a successful recipe in this challenge. So that's strange, though, because we've seen a lot of strong advancements across many different tasks, such as machine translation and speech recognition, question answering, and so forth. And across all these tasks, the models were basically based on some sort of sequence-to-sequence or encoder-decoder architecture. And the curious part, though, is that there are still a lot of difficult challenges remaining. For example, adversarial examples tend to break existing systems on QA and machine translation, but also in general, general document to summarization or data to text and conversation. All of these are difficult tasks, and somehow what worked really well for machine translation doesn't seem to generalize well for a lot of these tasks. So in this talk, I'm going to argue that the reason why we see this significant performance gap across different tasks is because they are really fundamentally different tasks. So there are tasks in type 1 case where there's a strong alignment between the input and the output so that it's possible to learn the mapping function f. And in these cases, surface pattern matching can go quite far. And in contrast, in the case of type 2 examples, like conversation and long-term text generation, the alignment between the input and the output is typically very, very weak. So it almost doesn't make sense to learn this mapping function. And usually, though, there's this rich context or background knowledge assumed in the way that people understand and generate text. And this background knowledge is also what's really fundamental in the way humans understand each other and read between the lines. So for example, when we see a news headline such as cheeseburger stabbing, if we give that to state-of-the-art parser, it's going to tell you that these are nouns. Cheeseburger is modifying the word stabbing, but that really doesn't explain what this headline really means. Does that mean someone stabbed a cheeseburger? Or a cheeseburger stabbed someone? Or cheeseburger stabbed another cheeseburger? And you know the correct meaning probably was something like someone stabbed someone else over a cheeseburger. So how did we do that? So it wasn't about just understanding what is in the sentence, but also about filling this missing information. You are able to reason about what may have been the correct interpretation by imagining that there are two people involved in this event, even though they were not even mentioned in the original news headline. This is the actual news headline. So the way it works, it seems that there are different types of common sense reasoning that we are doing almost effortlessly. And the first kind of knowledge is a physical common sense, that it's not possible to step someone using a burger, which is too soft. And the social common sense is that it's not okay to step someone, it's bad, and probably it's also newsworthy. So there has been a lot of research in NLP to learn a broad range of encyclopedic knowledge, like who's the president of which country, born in what year, under this research branch called information extraction. Now, we can make good conversation without memorizing all this. So there's a lot of different kind of knowledge missing in the current study, such as the naive physics knowledge that we just looked at, as well as the social norms or social common sense knowledge that we do rely on in day-to-day conversations. So the word common sense, however, is not new to us. It was really a hot research topic in olden days. However, if I search common sense in ACL Anthology, that's the repository of NLP papers, the papers are either from 80s or maybe a little bit from the past few years, but nothing in between. So in order to be taken as a serious person, we could have not used this word. Don't mention this taboo word. But I suppose people forget about the past failure eventually. So there have been some interesting recent challenge data sets that either explicitly require common sense or implicitly assume common sense, such as Winograd schema challenge or common sense story close task and others. And in all these tasks, language models that rely on surface patterns are not performing very well, no matter how much data you give. And it's extremely unlikely, at least in my mind, that brute force more data, deeper neural network will somehow do the magic. So we need somehow a different game plan here. I don't really have a solution, but today I'm going to present a fairly speculative thought about organizing at least some aspect of a common sense knowledge through language, especially this notion known as a frame semantics. So in modern NLP, the word frame semantics associate more with labeling predicate argument structure, the task also known as semantic role labeling. However, the original intended scope of frame semantics was much larger, broader, and frames in particular were a characterization of stereotypical scenes or situations that we encounter in everyday lives. And in recent years, our lab, as well as others, started exploring this thought. So that's going to be first half of my talk today. And then the second half of the talk is going to be about neural networks. I feel like I have to throw in some neural networks somewhere. So the first part, we start with verb physics. And this work was motivated with this idea of robots in the future being able to interact with us in an unstructured environment. And they need to be able to understand and reason about different physical properties of objects and actions. And in order to do that, it seems that we somehow need to acquire this knowledge. And initially, we thought maybe we should search Google. Now, the problem with searching Google is that nobody says that I am larger than a chair. In fact, nobody says any of this because it's trivially true. It goes against Grice's maxims. And so when people finally say something, the horse was as small as a dog, that's like an exceptional case. So if we learn from this, we will assume something incorrect about the world. So in order to overcome this reporting bias, at first we thought, let's look beyond the language, like computer vision. So 2 years ago, For example, we looked at a bunch of images and measured different object sizes, corrected that with depth, perceived depth, and mix that with language statistics and reason about different relative sizes. So we were able to do that and plus other types of physical knowledge. But quickly I realized not only NLP is hard, computer vision is also hard. And even though a lot of the physical knowledge about weight and strength and rigidness and speed, these are all visual to human eyes, but not as much to computer vision today. So then what do we do? Well, I cannot wait until I have a robot that can explore in the real world through interactions. So decided to come back to language, but try a different idea. So here's the key insight. Although nobody says any of this, people do say a lot of this, how you interact with different objects. And when you throw something, it's generally the case that you are bigger than the object, probably weighs more than the object, and as a result, the object that you just threw will move faster than you. So our idea here is to solve two related puzzles simultaneously. One puzzle about learning physical properties implied by actions, and the other puzzle about physical properties of different objects. Across 5 different physical dimensions, including size, weight, speed, strength, and rigidness. The representation we build over frame semantics is named as a verb physics, and it looks something like this. Given any verb predicate that's for actions, there are typically different arguments involved, and for any pair of arguments, we can learn the entailed knowledge about this physical dynamics. So, for example, we walked into the house would imply that the house is bigger than me. And when I said I squashed the bug with my boot, probably the bug is smaller than me, etc. So we can learn this sort of long list of different entailment knowledge that comes around this any given action predicate. Now, how does this differ from related work? So pattern-based information extraction or extracting knowledge from word embeddings are not going to be able to learn the kind of entailment knowledge that I'm presenting here because they rely on surface patterns essentially. And then there has been recent work for common sense knowledge-based compilation, especially based on ConceptNet. And again, existing knowledge base doesn't cover all this entailment knowledge that I just mentioned. And our work can complement vision or robotics-based grounding and also complement this recent effort that tries to extend frame semantics by presenting computational models. So the model, I'm going to just sketch out how we do, how we frame this knowledge acquisition problem as a collective inference problem. So what we are going to do is we are going to first define a collection of random variables, especially each object pairs get different random variable that looks at whether a particular relative object knowledge holds between a pair of objects. And for different verbs, similarly, we create different random variables that codify whether, for example, if x throws y, does that imply x is bigger or smaller or comparable to y? So we have a bunch of these random variables, and the value of the random variables are what we want to learn. Now, the verb variables, by the way, is in fact a collection of random variables representing different types of frame constructions involved for each verb. For example, x throws y is really different from x throwing up y, and so forth. So there's that. And the challenge here is that we don't have much evidence to support any of these random variables because nobody says my house is bigger than me, or when I throw something, I'm usually bigger than the object that I'm throwing. So what do we do? What's really cool is that because we assume both types of knowledge, the way we use language sort of implies the knowledge that you and I share. So there's plenty of evidence in the way action object interact. And in order to quantify that, we're going to then define potential functions between verbs and arguments, as well as between different types of variables that share or imply different types of knowledge together. So the underlying details are not overly important. However, the high-level view intuition is that we can encode this type of knowledge using probabilistic graphical model. And finally, there's going to be unary potential function for each individual node, some of which will include seed knowledge. So far, we've been only talking about size, but we can do this sort of a construction for other types of knowledge dimensions as well and connect them up. So the potential functions are basically parameterized through embeddings in a log linear form. And the inference, we use loopy-loop propagation. That's one of the standard techniques to use. And very briefly about what can we do with this graph formulation is that what's shown here is random baseline and majority baseline. If we learn this knowledge from just embeddings without any graph structure, then we do much better. But with the graph, we can infer or reverse engineer knowledge more accurately. So to summarize, the verb physics, this is just a visualization of the graph, presents our exploratory work to see whether we can reverse engineer some aspects of naive physics knowledge by solving two related puzzles simultaneously. And we have shown that we can do this even without embodied agents while we are waiting for it to actually work. And we can also learn knowledge that's not really visual to computer vision today. But that's really exploratory work. And there are many challenges that we need to address. For example, we want to see whether we can learn knowledge beyond these limited aspects of naive physics. And also, we want to be able to see some downstream use case. And how do we relate this for neural networks in the end? So I don't have very solid answer for any of these questions. However, I'm going to provide some partial answers or answers that are suggestive of some solutions down the road. So very briefly about the first 2 points, we have this recent work on zero-shot activity recognition by inducing verb attributes. So as a non-native speaker, I didn't know what swig means. So I looked up dictionary. It means to drink liquid in great gulps. Then I can visualize what this might look, even if I don't need to see any like 10,000 images in order to be able to see this. So I can certainly reason about different aspects of this action, like motion dynamics. Probably it's more motion than sleeping, but less motion than exercising. Social dynamics. What kind of effects does this action have on objects? What kind of body parts would this action involve? So using that, we have shown that we can reason about previously unseen actions. So yes, another example that I would like to show you is connotation frames. That's going to show you that we can cover knowledge that's really much different from naive physics or visual knowledge. So imagine computer agent learning about the world by reading news articles, but only pro-life news articles. So according to such news articles, Supreme Court refuses to hear blocking regulations endangers women, while Texas law protects lives and health and protect women. In contrast, the worldview, according to pro-choice articles, look as follows. The Supreme Court strikes down Texas law, which violates and imposes on women who want to make choices and have a constitutional right. So what's interesting here is that there are these different verbs creating really different framing effects, such that they can create or portray the hero, who's the heroes and who are villains in our world. And also they can project different types of biases, some of which may be unwanted. So women on one side is portrayed as someone who's powerful, whereas the other one portrays as themselves in distress. So in order to be able to study this sort of connotative effect coming from any given action or verb predicate, we designed this connotation frame that goes as follows. For a verb violate, agent is doing something to the theme, and the likely sentiment toward each other is negative. And what's important here is that even though writer and readers are not mentioned, we can also reason about what they would think about agent and themes in this event. So probably writers are negative toward the agent and more supportive toward the theme. So similarly, we can think about the fact that whatever happened to the theme is negative, and as a result, the theme is unhappy about that. And intrinsically, the theme, whatever gets violated, is something valuable because it doesn't make sense to violate to something garbage. So we can think about all this sort of a polarity assignment across the different types of value judgments and implied effects. And using this idea, we can then think about what would left-leaning sources typically report? Obama criticizing someone, or Obama is criticized by someone? I mean, you can use either way, really, because the use can be contextual. However, what do you think will be more common use? Obama criticized someone, or the other way? The other way, a little bit more. So the other way, because the act to criticize is quite harsh. It's almost a little too much. So if you want to support Obama, you want to rephrase it, to soften it a little bit. So that's indeed what people do, what journalists do. Oftentimes, Obama gets criticized by someone else according to left-leaning sources, whereas right-leaning sources will say that Obama is the agent who criticizes someone else. Same goes with the attack. So we are basically taking this Wittgenstein's view here that the meaning of a word comes from the way people use that word in similar context. So even though both naive physics type knowledge as well as connotation are fundamentally contextual, we can still learn and reason about the likely interpretation by looking at a lot of language use cases. So as far as computational model, we do something similar to before, that we have these vector graphs and the probabilistic reasoning. And I'm going to just move toward interesting use case that came out of this about power and agency in modern films. So we all have heard that there are biases in modern films. That's not a news. There's also this Bechdel test that tests whether there are at least two women talking to each other about something other than a man, and only 40% of movies out there pass this test. But to be honest, this test is not very informative because Cinderella can pass this test. I mean, the Snow White. So we all know that Cinderella is not necessarily the most ideal portrayal of women. She lives and goes, sees and hears and appears, etc. These are fairly low agency activities. The new movie, Frozen, has this character, Anna, who's maybe better, but still what she does in a large chunk of the movie is still pretty passive. She gets injured by someone and gets proposed by someone, etc. Whereas Elsa is the one who objects and unleashes power and destroys things and does things. So in order to be able to study this sort of connotative effect that's assumed by language, we extended our previous work to add agency dimension, that's a unary relation about whether the action implies high agency or not. And then power dynamics, this is binary relations that implies, like demanding, for example, if I demand, I imply that I have a higher power, whereas begging would be the other case. So using this, we were able to study these plot summaries of these movies, and we were able to show that indeed Elsa shows a higher power compared to these two other characters. So this presents us really good opportunity for doing something about the problems that we keep talking about, especially bias in AI, which is in part because of bias of humans. So we can continue working on building models that can not only avoid bias in machine-generated text, but also identify and correct human biases in language. And a related task could be detecting fake news in the sense this is about understanding the hidden intent of a people, and this is something that we could study further. So as a quick summary, I have presented a representation formalism that encode different types of social common sense. It's limited, but still the kind of knowledge that have not been captured in prior literature, organized as a frame-semantic knowledge. So now let's move to the second part, which is going to be about some neural network stuff. And our work is based on iClear paper that just got accepted. And our work was originally started with this idea of, can we somehow learn to generate recipes? And we thought that because it seemed like a cool task, and in fact, this was one of the old AI challenges. And we thought that we should somehow parse raw text, build graph representation, and then abstract away prototypical recipe structure, out of which we sample a graph out, and then translate that to raw text. So we worked on the first segment, even wrote a paper about that. However, the remaining was not that easy. So we worked on this for a while, and we're wondering, I don't know about this long chain of small steps. Can we somehow do it in one shot? So that's also when we heard about this amazing encoder-decoder architecture that, if you apply it to any task, you get to write a new paper. It works really well for machine translation in particular. So we decided that we're going to encode recipe title and generate the recipe out. Sausage sandwiches given to some sort of RNN language models came out as such. Yeah, I'm sorry that if RNN was your favorite language model, it's still a favorite language model of mine. However, it's not very good with long-term context. It eventually recovers from the sandwich overdose, but it has to repeat a lot of things twice. So locally fluent, but globally incoherent. So then we designed a new architecture that I'm not going to present today, but it's got this cool name, neural checklist models, that can present much better recipe. But it's better, but it's not perfect. So wash and dry the cauliflower, heat the oil in a skillet, fry the sauce until they are golden brown. Yeah, some of you noticed that there's a problem. So forgot to cook the cauliflower. It's almost coherent, though. So when I presented the neural checklist model at Harvard University, a student asked me whether I think RNNs are a mouth without a brain. And I didn't have a very good answer then. I mean, it's kind of, she had a point. So that motivated us to really think about how do we somehow emulate the ability to read between the lines and reason about the unspoken but obvious facts. So encoder-decoder architecture, especially the vanilla sequence-to-sequence models, are not really designed to learn and reason about the implied causal effects. Like When you fry tofu in the pan, you implicitly change the location of the tofu to the pan if the tofu was not already inside the pan. Still, one doesn't need to say that out loud, you do that. The temperature of the tofu will become hot. The tofu will be more cooked than before. So we wanted to explore this idea of text understanding by simulation, especially simulating the causal effects implied by text, focusing on not only what's said, but also what's not said, but obviously implied, abstracting away the surface strings. And our model shares a similar spirit with some of this earlier work, such as recurrent entity networks and memory networks. This contrasts with more commonly studied approach where text understanding is operationalized as a labeling task, which tends to focus on just labeling words that appear in a sentence. So this is a very useful way of understanding text. However, what we want to explore here is to complement this much better studied way of understanding text. So to do that, we start with this encoder that typical sequence-to-sequence model will have. But after encoding a sequence into a vector, we're going to have this action selector that selects what action to apply, and then what entities to apply the action to. We're going to look this in a bit. And then there's going to be simulation module that applies the action to entities such that we can then reason about what happened to different entities. So let's go over each of them one by one. So starting with action selector, after reading a sentence, we are going to attentively select and compose what action to apply. So when we see a word like fry, we could potentially select just the word fry, but maybe we want to mix that with just a small bit of the word meaning put, because maybe you want to change the location of it. Similarly, when there's a word like a saute, which maybe I never learned before, but by reading the definition of that word, I can compose in my mind what kind of actions I need to execute in the kitchen. So it's almost like the elementary actions are already there. There's a fixed number of them, but language is richer, and we can describe different actions through composition. So for entity selection, we also select entity attentively by looking at the current sentence. But in the case of entity selection, it's also important to be aware of what happened in previous sentences, because there may have been some other entities that were involved and assumed to be involved in the following sentences. So we do that both using direct sentence attention as well as recurrent attention. And then finally, the simulation module is just a simple matrix operation where, given the composed action and entity representations, we want to predict the resulting entity such that when we query that entity, it can explain what happened to them using natural language phrases. This is because we cannot actually have a simulation environment in which this cooking really does happen. Even if we were to build that, it's still sort of like categorical in the way that we treat these state change representations in our model. So given that, now that we have these updated entities, we can go back and write over this memory structure that stores and tracks what happens to different entities over time. And that completes our model description. So there are different types of prior knowledge baked into our network structure. First of all, there's this inventory of actions and entities that are acquired, in our case, automatically from the training corpus. And it's important to note that we only just use this to create the placeholders to store these embedding representations of actions and entities, but their representations are learned from the model. And then, in addition, there's inventory of causal effects. Now, this part is a little bit harder to learn automatically, so we sort of relied on human intuitions, especially by crowdsourcing this. And we selected or organized what we crowdsourced into 6 simple dimensions, including composition, cleanliness, cookedness, temperature, shape, and location. This may seem a little bit arbitrary, but it can be extended for other types of dimensions as well in the future work. And then finally, the action, simulation module, the application module, is sort of reflecting our intuition about how actions tend to have this frame-semantic type representations when we think about their causal effects. So this is our way of exploring how we could somehow bake in the kind of common sense knowledge that we discussed in frame-semantic type representations to neural models. And by doing so, we can make this neural architecture more interpretable and easier to understand. So for the data set, in our study, we focused on cooking recipes because it's a natural data set that describes processes and action causalities. It's including rich natural language, but still reasonably in a confined domain, so that it's a nice first step toward exploring a model like this. And now the challenge is that we don't have an actual simulation environment. Like the success of AlphaGo 0 really relies on the availability of a simulation environment where you can try a million things and then get very precise reward information, which we don't have here. Nor do we have human low-level annotations, because we tried to do that. It's very expensive. So we still collected manual annotations, but just so that we can use that for evaluation purposes. So the only reasonable option left at that point seemed like learning with distant supervision, where we loosely label these simulation steps using simple heuristics, and then design a loss function that is composite of different types of simulation steps, as well as some sort of a discourse level coherence term that allows the learned model in the end can generalize beyond what we provided as noisy heuristic labels. So for the evaluation, we have both intrinsic and extrinsic evaluations. For the first part, we basically inspect whether the simulations make sense. And for that, we have 2 baselines. The first one based on some modified version of gated recurrent units, which represent neural network architecture without an explicit memory structure to track dynamic entity states, and also without explicit modeling of action causality. Another obvious baseline to use was recurrent entity networks. Again, we had to modify this to work better for our task. This one represents the version with external memory structure for tracking dynamic entities, but without having explicit action representation that can simulate action causalities. So for the entity selection, we found that our model does better than these baselines. And for state tracking, which requires correctly selecting entities and then also being able to predict what happened to them, we will also be able to improve better. And we can also inspect whether learned embeddings make sense. And we found that, for example, the nearest neighbor of the action cut include slice, split, snap, etc. So they sort of make sense. What's interesting about boil is that the most similar words are cook, microwave, fry. And these are not the same as the kind of the most similar words that you find from pre-trained word embeddings. So our model learns causality-driven similarity of actions. So this is just evaluation based on inspection, but this learning, sort of like being able to reason about what happened to different entities, actually have a useful effect on some downstream task. So we tried using this memory block that tracks dynamic entities as an additional input for the task of recipe generation and for different types of evaluation measures. We were able to show that our new model performs better than other alternatives. So to summarize, I presented the work that explores this idea that perhaps we can try to model language understanding through some sort of implicit simulation, which is using the word simulation a little bit perhaps differently from traditional meaning of a simulation, but somehow what I mean by this is the ability to explain what happened to different entities and reason about the unspoken facts that are obvious. And that can complement much better studied way of understanding text by labeling words that appear in text. So to conclude, I think that despite a lot of recent success with the deep neural networks, it's unlikely that what worked really well for some task will generalize over all tasks, especially adding just more data, more layers, and training it somehow better. It's not clear whether some sort of a common sense knowledge will arise from deep neural layers. And so we may revisit what people thought about common sense or frame semantics in the past and see whether we can give new computational representations to it, both by studying frame semantics more directly, but also by designing new architecture that can incorporate such knowledge. Thank you.
Thanks for the nice talk. I had a clarification question on one of the results that you showed in the first part on the common sense. You had this example that a lot of common sense knowledge, they're often not written directly on the internet. I was wondering, in your evaluation, when you're evaluating the result of your models to retrieve common sense knowledge, how much of your evaluation was those kind of sentences that are often not written on the internet? Like, for example, often a tree is taller than human. It's not written anywhere, but like, did you have these kind of things in your evaluation set? Like how much of the things that you learn from images, they're actual hard to retrieve common sense and not the obvious things?
So I think the question was how much of this knowledge covered by the first part, the verb physics, was actually not really there. And we don't have numbers. I don't have a number right now. But I expect that for object-to-object relations, sometimes there are such pairs. Like people, we may be able to see that dogs are usually bigger than cats. It's unlikely that you see comparisons between very, very different objects, however. For example, elephants are bigger than butterflies. People just don't say that. For action entailment, by and large, they are not really mentioned anywhere in text.
Hi. Thank you for the nice talk. I was wondering if the tasks you described could use the knowledge in the psych knowledge base.
I couldn't fully hear your question, sorry.
I was wondering if the tasks you described could use the knowledge coded in the psych knowledge base.
Oh, psych. So that's a great question. I don't have access to psych. There may be some in psych. I checked ConceptNet, and there were many not in ConceptNet. But in any case, one thing that I didn't talk about here, but I think some people did try doing, is to learn using this sort of a common sense knowledge base and learn embeddings out of it and be able to use that for some sort of a downstream task.
Thank you. Could I ask a second question?
Not sure if I answered your question, though.
I know, thank you. Could I ask a second question?
Sure.
You chose a very difficult topic even for humans, cooking. I send recipes to my daughter. She is human, she has cooked, but she still comes back with a million questions. They are inherently vague. There is no perfect recipe. It will miss something. Just a comment.
Well, I totally agree with your daughter. I have the same problem with my mother.
Hi, perhaps this is an obvious and natural question, but I'm just going to act like an instrument to bring this topic up. So, recipe generation is a sequential generation kind of a task, so perhaps it's your next idea would be to try to use this model for dialogue generation or management as well. Do you have any thoughts and comments on that?
Yes, so we were definitely motivated by the dialogue generation, especially given that we competed for the Alexa challenge. It turns out it requires a little more time than 1.5 years, so we haven't gone too far yet, but we're definitely working on it. I think that for dialogue, it doesn't need to cover really a lot of different types of social common sense knowledge beyond what I presented in this talk. So in that sense, what I presented here is more of an initial study. But my hope is that we can do this at a much larger scale, and we can design better models to be able to achieve that goal down the road. We have to try.
Yeah. Okay. A tangential question: do you have any criticisms on the use of generative adversarial networks for generating dialogues as well? Do you have any criticisms on the research direction of the community in trying to use GANs for generating natural language dialogue?
Oh, do I have any criticisms against the GANs? No, I don't. I mean, it's a very interesting model, and in fact, we're also playing with it. I don't know, though, whether GANs will be able to actually make a dialogue with humans even more than 1 minute down the road. I mean, I think it's a really interesting interesting model for sure, but it feels like there has to be something more than that.
Yeah, I sort of agree with you. Thank you so much.
Hi. First of all, thank you for the great talk. And so I have a question about the procedural knowledge in terms of the natural language and, for the recipe. So that particular example you provided, actually except that the cooking part is missing, the first part, that in the preparation, the last part is all it's all pretty good, like results already. I wonder whether there's any way to identify whether the subtask or subsequence is actually that makes sense. But even though generating a long sequence is difficult, but the partial sequence can be useful for certain tasks. Whether there's any way that to identify that partial results is useful for certain tasks.
So I think the question is, can we automatically measure the quality of partial sequences? So I think we could do that to some degree, maybe by matching the partial sequence to the original recipe through either like machine translation measures like BLEU and rouge, which, by the way, are not really perfect measures, not only for machine translation, but also for text generation. But also, we can check more like information extraction style evaluation, where we try to find whether particular actions have been applied or not. But these being all automatic, usually when there are paraphrases, it may or may not be correctly evaluated, so it's difficult. We found that in our study that we can try to automate that. It may correlate with human evaluation to some degree, but it's not quite perfect.
Thank you.
Hi, my name is Judy Goldsmith, and I don't work in NLP, so I may be asking a question that's well known. I was struck in your diagrams about abortion that there was this quantitative measure possible of dissonance in the discourse, disagreement. Is that something people are looking at as a way to look at civil discourse?
Yes, so in general, for understanding connotation in particular, this precise understanding of the discourse context is important, and people have done such research. In our work, we were exploring this idea that we may be able to study this as lexical semantic knowledge as well, so I sort of glossed over that part. But yes, people definitely have been looking at contextual understanding.
Thank you.
Hi, thanks for the talk. So in the first part of your talk, you mentioned about how to extract the common sense from the neural networks. So I'm wondering, have you thought about do the other way around, like incorporate some common sense as some prior constraints to train the neural networks, because that probably can save some data-hungry problem of the neural networks.
Yes, that's a really great point. So I wish someone works on that, and or I wish I had an idea how to achieve that. But it seems that for like dialogues, for example, it's a really one challenge that we had in the competition with Alexa is that it's hard to get exactly the right kind of data. There's a lot of data out there, but they're just different from the kind of a dialogue that we are supposed to be able to carry on. So in order to address such challenge, somehow better representing different types of knowledge and then having better initial start with any training seemed like the desirable research direction for sure. Don't have a solution in mind yet.
Thank you.
Hello, yeah, thanks for the nice talk. I had a question about the recipe generation work. So I imagine at some point you might want to kind of cross the reality gap and create cauliflower that's cooked. I wonder if you've thought about the human-machine interaction part or kind of like a reinforcement learning part where you would want to actually get feedback from how it actually went in reality to create a usable recipe.
Right, so having such mid-step feedback will definitely be useful for learning better algorithm. And we thought about it. We haven't really worked on it with human interaction, actual human interactions, but that's a great point.
Hello.
Yes.
I actually don't have a question. I just wanted to say thank you very much for such a lovely talk, and thank you for doing it even though the music next door was so ridiculous. You did a lovely job.
Thank you.